I am Eddie Lentz. I am in Dr. Hall's 344 Mechanical Design Section 1, and I am doing the rework for Problem 4 on Midterm 1 exam. Problem 4 pertains to Castigliano's theorem, and more specifically, use Castigliano's theorem to prove the vertical deflection of a steel column standing upright under its own weight. Assume a length of 25 meters, a cross-sectional area of 0.125 meters squared, and with a hint of we will need the weight of steel, which is 76.5 kilonewtons per a meters cubed. First off, it is important to realize the type of strain we have present. Seeing in the problem, we're to compute a vertical deflection. It's asking for a strain in more ways than one. A column standing under its own weight, meaning there will be purely a vertical force present and will adhere to axial strain. At the top, I wrote an external force of, it looks like an external force of F, although I am only using it to prove that the force present is going to be proportional to the weight of the steel column itself. To solve for a relation for F, it is important to do a unit analysis in order to find a relation for just F in kilonewtons. Since it is kilonewtons per meters cubed, if we multiply by a volume, we will then have a force. Since we are not explicitly given a volume, but instead an area and a length, we can multiply that weight times the area times x. The reason why I'm leaving it as x is so that we can integrate and account for the increase in force as we go further down the beam. This will then increase the axial deflection. Plugging in, we have a force equal to 9.5625x. Now, to begin the problem, we will start with the strain in the axial direction, equal to force over AE, the area times the Young's modulus of the material. And then, to find we will integrate that strain and multiply by the partial derivative of F, with respect to F initial. This will be equal to the deflection. What is important is to apply partial derivatives before plugging in for F. This is so we don't end up with a zero canceling out everything in the integral. If we plugged in for F, we would have 9.5x with respect to F would yield a 0. So we're going to leave it as F. Solve the partial derivative. We're going to have the axial deflection is equal to the integral of 0 to L times 1 over AE times F times 1. Now we are ready to plug in for F. Plugging in for F is going to give us an axial deflection of pulling out constants 1 over AE times the integral of 0 to L 9.5625x dx. Using the reverse power rule, we're going to add 1 to that exponent of x and then divide by that exponent of x, so 2. And then we are going to evaluate over x equals 0 to x equals L, which is equal to 25 meters. Coming down, we will plug in 25, which fully written out will be 1 over A, 0.125 meters squared, times E, 207 times 10 to the 9th gigapascals, obtained from the tables in the test for plain carbon steel, multiplied by the 9.5625 over 2, times the x25 squared. We can plug in minus the integral evaluated at the lower bound, 0. We will get a subtracting 0. It is non-trivial, or it is trivial. This will give us a axial deflection of 1.15 times 10 to the negative 7th meters. Now, previously on the exam, I used F equals mg and attempted to solve for F as an external force. What immediately goes wrong is plugging in F equals mg when attempting to take the partial derivative of mg should have yielded 0. Instead, I wrote mg again and ended up with a force squared in my final answer. Thank you.